This is an online learning (LMS) project. The thought course is EE 301 Communication Systems. Whole material of this course is redacted then dubbed by an American English-speaking TTS, text-to-speech, software, and put into this slideshow with animations for students to easily follow and understand. Instructor, Dr. Ali Kara. Content: periodic signal, power signals, Dirac delta function. Fourier series, Fourier transform, of periodic signals. Sampling function, rectangular pulse train. Parseval's power theorem. If you want to check your background, or want to know more about these topics in detail, see EE 303 Signals and Systems lecture notes. Periodic signals, sinusoids and phasors are periodic signals. These class of signals obey the following relationship: V of t plus minus m t0 is equal to V of t, where t lies between minus and positive infinity. This equality implies that the signal V is periodic with period t0. Average of a periodic signal is given by 1 over t0 times integral over t0 of V of t integrated with respect to t. Communication signals are considered as either voltage or current type signal. When a resistance R equals to 1 ohm is considered, the normalized average power, denoted by P, is 1 over t0 times integral over t0 of square of absolute value of V of t integrated with respect to t. Question: periodic signals, power signal. Find the normalized average power of the following signal: cosine 2 pi f0 t, where f0 is equal to 1 over capital T0, 1 period of the signal. Solution: normalized average power of a periodic signal is equal to its magnitude square, integrated over 1 period. Look at the appendix formula sheet to find the identity cosine square. Then, based on your knowledge from Math 157 and 158, solve the integral. The result is 1 over 2. Question: periodic signals, Fourier transform. Find the Fourier transform of the following functions and write their magnitudes and phases explicitly. X of t equals cosine 2 pi t, y of t equals sine 2 pi t. Solution: for the Fourier transform of common functions, please refer to the Fourier transform tables that can be found in your textbook, on the internet, and lecture notes. The magnitudes of their Fourier transforms are equal to each other. They differ only in phases. Phase of a complex identity can be found by taking the arctangent of imaginary part over real part of the complex identity. Dirac delta function. In mathematics, the Dirac delta function is a generalized function. On the real number line it is 0 everywhere except at t equals 0, with an integral of 1 over the entire real line. The delta function is sometimes thought of as an infinitely high, infinitely thin spike at the origin, with total area 1 under the spike. Physically, it represents the density of an idealized point mass or point charge. Its Fourier transform is simply equal to 1 for all frequencies. For the delta function to have meaning, however, it has to appear as a factor in the integrand of an integral with respect to time. And then, the other factor in the integrand must be a continuous function of time. Let x of t be such a function, and consider the product of x of t and the time-shifted delta function Dirac delta of t minus t0. We may express the integral of this product as follows: integral from minus infinity to plus infinity of x of t times Dirac delta of t minus t0 integrated with respect to t is equal to x of t0. It is also called the sifting property. As you can see, Dirac delta function sifted the continuous time function x of t so that the outcome is x of t0, t0 being any time point on time axis. Noting that the delta function is an even function, we may write x of t convolution direct delta of t is equal to x of t. Direct delta functions time and frequency domain representations can be seen here. As clearly seen, while in time domain the direct delta has only non-zero value at origin, in frequency domain it occupies all of the spectrum. Question: direct delta function. Evaluate the following expressions: cosine t convolution direct delta of t, sine t convolution direct delta of t minus pi, sin t convolution direct delta of t plus 1. Solution: direct delta's sifting property will be used here. Direct delta function as a Gaussian pulse. Consider a Gaussian pulse of unit area, defined by g of t, 1 over tau times exponential of minus pi t square over tau square, where tau is a variable on pulse width. The Gaussian function g of t has two useful properties. 1. Its derivatives are all continuous. And 2. It dies away more rapidly than any power of t. The delta function is obtained by taking the limit as tau goes to 0. The Gaussian pulse g of t, defined here, is the same as the normalized Gaussian pulse exponential of minus pi t square, except for the fact that it is now expanded in time by the factor tau and compressed in amplitude by the same factor. Therefore, applying the linearity and time-scaling properties of the Fourier transform to the corresponding transform pair, we find that the Fourier transform of the Gaussian pulse g of t is also Gaussian, as shown by capital G of f, which is exponential minus pi tau square f square. It is clear to see from the graph and analytical formula that, as tau goes to 0, the capital G of f curve gets flat and tends to be constant at G of f equals 1. Question: direct delta function as a Gaussian pulse. Find and plot the Fourier transform of the following signal for tau equals 0.25, a short pulse, and tau equals 2, a longer pulse. G of t equals 1 over tau exponential minus pi t square over tau square. Solution: the result indicates that a shorter pulse occupies a larger bandwidth, and vice versa. Direct delta applications. DC signal and frequency domain. By applying the duality property to the Fourier transform pair of direct delta function obtained several slides earlier, and noting that the delta function is an even function, we obtain the Fourier transform pair. Constant 1 in time domain has the Fourier transform of direct delta of f in frequency domain. We can conclude that a DC signal is transformed in the frequency domain into a delta function occurring at 0 frequency. Complex exponential function. Next, by applying the frequency shifting property, we obtain the Fourier transform pair of exponential minus plus j2 pi fc t in time domain and direct delta of f plus minus fc in frequency domain. Note that the sign of the exponential argument and center frequency in direct delta is reversed. This equation states that the complex exponential function is transformed in the frequency domain into a delta function occurring at frequency fc. Sinusoidal functions. Consider next the problem of evaluating the Fourier transform of the cosine function. We first use Euler's formula to write cosine of 2 pi fc t as 1 over 2 times, in parentheses, exponential j2 pi fc t plus exponential minus j2 pi fc t. We use the previous result of complex exponential function to get the Fourier transform pair cosine 2 pi fc t in time domain and 1 over 2 direct delta of f minus fc plus direct delta of f plus fc. It is also clear that sine function can also be represented in this manner. Sine of 2 pi fc t in time domain has the Fourier transform of 1 over 2j direct delta of f minus fc minus direct delta of f plus fc. Take a look at the time and frequency domain graphs of sinusoidal functions. Question: direct delta applications. Find the Fourier transform of the following signals: 1 plus cosine 2 pi 10,000 exponential j 2 pi 10,000 sine 2 pi 10,000. Direct delta applications. Unit step function. Remember how the unit step function was defined? It takes the value positive 1 for t is greater than 0, it is 1 over 2 for t equals 0, and it is 0 for t is less than 0. Remember signum of t, we can write unit step function in terms of signum function. U of t is equal to 1 over 2 times signum of t plus 1. We employ Fourier transform to the unit step function, written in terms of the signum function. Using the linearity property of the Fourier transform and the corresponding Fourier transform pairs of, we find that the unit step function is represented by the Fourier transform pair 1 over j2 pi f plus 1 over 2 times direct delta of f. This means that the spectrum of the unit step function contains a delta function weighted by a factor of 1/2 and occurring at 0 frequency. Fourier analysis, Fourier series. It is well known that by using the Fourier series, a periodic signal can be represented as a sum of complex exponentials. Also, in a limiting sense, Fourier transforms can be defined for complex exponentials. Therefore, it seems reasonable that a periodic signal can be represented in terms of a Fourier transform, provided that this transform is permitted to include the LTA functions. Decomposition of a periodic power signal into sums of sinusoids, or complex exponentials. Let g subscript t0 of t be a periodic signal with a period of t0. Then gd0 of t can be written in series form as the summon from minus infinity to plus infinity, Cn, exponential j2 pi n, f0, Tcn are called complex Fourier coefficients. In theory, we must find infinite number of coefficients to fully decompose our signal into a Fourier series. However, we will see later in this slideshow that, with a relatively small number of coefficients, say for example n equals 40, we may decompose our signal into a Fourier series with a negligibly small error. Cn can be evaluated by the following equation. Cn equals 1 over d0, integral over d0, of gd0, of t, times exponential minus j2 pi n, f0, t, integrated with respect to t. In this composition, f0 is called the fundamental frequency, which is equivalent to 1 over d0. Integer multiples of the fundamental frequency are called harmonics. For real signals, we have the decomposition as follows: gd0 of t equals the c0 plus the summon from 1 to infinity absolute value 2cn times cosine of 2 pi n f0 t plus argument of Cn argument, or rather arg of Cn, is equal to inverse tangent of imaginary part of Cn divided by real part of Cn. Question: harmonics. Fundamental frequency of a Fourier series is 5 kHz, with a unity amplitude. Find and plot its second and third harmonics, along with the fundamental frequency component. Take the amplitudes of the second and third harmonics as 0.7 and 0.2, respectively. Solution: see that components with larger frequency tend to get smaller in amplitude. Question: Fourier analysis, Fourier series. Find the argument of the following complex Fourier series coefficient. Cn equals 10 times e to the power j pi over 4. Solution: by Euler's formula, write the real and imaginary parts of the signal. Then use the arc tangent to get the argument of the complex coefficient C, and, alternatively, Hence Cn is written in phasor form, pi/4, which is 45 degrees, is the right answer that can be read directly from the coefficient given in the question. Periodic signal, ideal sampling function, impulse sequence. An ideal sampling function, or Dirac comb, consists of an infinite sequence of uniformly spaced delta functions. We denote this waveform by Dirac delta d0 of t. It is expressed as the sum m from -infinity to +infinity Dirac delta of t minus m d0. This ideal sampling function has a Fourier transform equal to f0 times the sum n from -infinity to +infinity Dirac delta of f minus n f0. This equality states that the Fourier transform of a periodic train of delta functions spaced 2 seconds apart consists of another set of delta functions weighted by the factor f0 and regularly spaced f0 hertz apart along the frequency axis, as seen in the figures. Rectangular pulse train. Remember from previous slides that how we decomposed a periodic signal and show it as Fourier series. For the real signal case, the idea was to find the relevant coefficients Cn and sum them after multiplying with the corresponding cosine function. Now, consider the rectangular pulse train as the signal to be represented in Fourier series. Rectangular pulse train V of t is defined as 8 times sum k from -infinity to +infinity rect of t minus k t0 over tau, where a is a real scalar constant, t0 is the fundamental period, and tau is the pulse length. We use this integral to find the corresponding coefficient Cn. Solving the integral yields Cn as a times tau over t0 times sinc of n f0 tau. We may write the first few coefficients like this. As you can see, knowing that Sinc function decays to 0 as its argument grows bigger, the contribution of the higher order coefficients will be small, and we can express the Fourier series with a finite and relatively small number of coefficients without losing much in the way. Question: rectangular pulse train. Find the first 3 coefficients, C0, C1, C2, of the following rectangular pulse train, with the following parameters. Rectangular pulse train. Take tau over t0 as 1/4. Now, we shall see how we will represent the Fourier series expansion. Absolute V of t now can be written in Fourier series form as a/4 plus √2a over pi cosine of omega 0 t plus a over pi cosine of 2 omega t, and so on. Rectangular pulse train. Now, we shall see how the Fourier series representation works for the rectangular pulse train signal. Amplitude of V of t is expanded through the 40th term. The last term is coincidentally 0. By taking the number of terms to the infinity, the Fourier series representation gets closer to the actual rectangular pulse train that it represents. You can see this approximation by the graphs, which have different number of terms in them. Rectangular pulse train. Now, we will see how we can take the Fourier transform of the Fourier series so that we can represent our function V of t in frequency domain as well. We can define the ratio of tau over t0 as the duty cycle. This definition is frequently used in pulse-shaped periodic functions, so it is beneficial to keep that in mind. Each term in the Fourier series, 2Cn, cosine of 2 pi n, fct, has a Fourier transform, a tau over t0, times sinc of n, f0, tau, times Dirac delta of f plus minus n, fc. So each term in time domain has 2 components in frequency domain at plus and negative fc. Rectangular pulse train. Now let us draw V, F, V, F. Terms can be calculated by the formulae. Tau over t, 0, sinc, n, f, 0, tau, times direct delta f minus n plus n f c. Question: rectangular pulse train Fourier series. Using the following coefficients, write down the Fourier series for the rectangular pulse train. Cosignal, temporal versus spectral. Cosine function can be written as 2 direct deltas centered at plus and minus center frequencies. Here, you can see the transformation analytically on the graphs. These graphs are generated using a physical signal generator and oscilloscope, temporal versus spectral. Now, we shall see the time and spectral forms of the rectangular pulse train. We take the duty cycle as 1/2 for visual convenience. See each term represented on the spectral graph. These graphs are generated using a physical signal generator and oscilloscope. Parseval's power theorem. Consider a periodic signal v of t, with a period of t0. According to Parseval's theorem, the average power of a signal can be found by this integral equation. Average power of v of t is equal to 1 over t0 times integral from minus t0 to plus t0 of square of absolute value of v of t integrated with respect to t. Another way of finding the average power is to use Fourier series coefficients. Average power of v of t is equal to the sum from minus infinity to plus infinity Cn times complex conjugate of Cn. This also equal to the sum from minus infinity to plus infinity square of absolute value of Cn. This says that average power can be found by squaring and adding the heights of the amplitude spectrum lines. Question: Parseval's power theorem. Assume that we have a signal whose all Fourier series coefficients are given below. Find its average power. Solution: take the square of all the terms and add them up. Note that, although it may seem unrealistic that so few terms can make up a signal, in practice, a reasonably low number of coefficients may be sufficient, as the larger coefficients become smaller and smaller and can be neglected.